Okay, this next section we're going to talk about expected value and probability distributions. First thing we want to mention is a random variable. A random variable is a function that assigns a number to each simple event in a sample space. So you might remember functions from algebra where you plug in a value, like here you might plug in a number like 2 and then the output would be 8. Well, a random variable is a function where you plug in a simple event. So the simple events actually represent the domain, and then the output can be some number. So that's what a random variable is. Let me just give you an example. Suppose we toss a pair of 6-sided die, and we're interested in the sum of the dice. Well, let's let S represent the set of all 36 possible outcomes. We could assign the random variable to represent the sum of the simple events. Now, I'll just give you enough to give you an idea. So consider these simple events, 1, 1, 3, 3, 4, 3, 6, 3, and so forth. Well, if we plug in 1, 1, since we already said verbally our random variable represents the sum of the die, then if we roll this simple event 1, 1, then if the input is that simple event, then the output would be their sum too. If we roll a 3, 3, the output would be the sum of 3 and 3, which is 6. If we roll a 4, 3, the output would be 7. 6, 3, the output would be 9. 3, 6, the output would be 9. And 5, 6, the output would be 11. And then 6, 6, the output would be the sum of 6 and 6, which is 12. So the input values are the possible rolls of the dice, and the output values are the sums, which are 1 through 12. Actually, that's not 1 through 12. You can't get a 1. It's actually 2 through 12, so not 1 through 12. Okay, so those are the sums you can get. Now let's look at another experiment. Suppose a pair of cards is selected from a standard deck. Suppose we're interested in the number of aces we select. Well, we can let S represent the 52 choose 2 or 1326 possible 2-card hands or 2-card selections. And let X be the random variable that represents the number of aces selected. So let me just randomly pick some 2-card hands. Let's say you get the 7 hearts and the 8 of spades. Well, if you plug this into the random variable, now since the random variable represents the number of aces in the hand, the random variable would equal 0. If you plug this in, again, the random variable would equal 0 because there's no aces. And here the random variable would equal 1 because there's 1 ace. Here the random variable would equal 1 because there's 1 ace. And then in these last two, the random variable would equal 2 because there's 2 aces in each of those. Now this time I didn't show you the little parentheses notation, but basically I'm still plugging in each of these simple events into the random variable. So in this, the input values are the possible 2-card selections, and the output values can only be 0, 1, or 2. Experiment 3. Suppose we answer 3 multiple choice questions that have 4 possible answers each, A, B, C, and D. S would be the set of 64, and I got that by just saying 4 times 4 times 4 possible answer sheets submitted. Let X be the random variable that represents the number of correct responses in a submitted answer sheet. Now, consider these answer sheets: AAB, AAA, BAC, BCB, CCA, and BCA. Now, let's suppose the key is in this order, BCA. So, if you're going to answer 3 questions, could someone get 0 correct answers? Sure. Could someone get 1 correct answer? Yeah. 2, 3, not 4 though, because there's only 3 questions. So you could get anything from 0 to 3. So I've got that written right here. You could get 0, 1, 2, or 3 correct answers. Where's my... There we go. 3 correct answers. Now, so basically, we're saying that X can be anything from 0, 1, 2, or 3. Now, if you submit, for example, if you submit this set of answers, A, B, C, well, remember the answer, the key is BCA, so we missed them all. We missed all three. So that would give you a random variable assignment of 0. If you answered AAA, you would get a random variable assignment of 1 because you got the last one correct. And for instance, if you answered BCC, then you got the first two correct, so X would equal 2. And then let's just go to this one. That should say BCA, shouldn't it? The key is BCA, right? So to get a 3, you'd have to turn in this answer, BCA. Okay? So anyway, that's an example. Hopefully that helps you understand what a random variable is. Now, let's continue with the above example. All right. The key is BCA, and the values of X are 0, 1, 2, or 3. Can we determine how many ways X could be 0, X could be 1, X could be 2, or X could be 3? Let's do it. To get no correct answers, to get no 0 correct, we must answer each one wrong. There's actually 3 wrong answers each time. So we would have to answer the first one wrong, so there's 3 ways to do that. The second one wrong, there's 3 ways to do that. And the third one wrong, 3 ways to do that. So there's 27 ways to get none correct. Okay? So in other words, there's 27 different answer sheets we could turn in to get none correct. Now, the next two, it's a little bit tricky. Basically, on the next two, you have to get 1 correct and you have to miss 2. So that means you're going to, on one of the questions, there's only 1 choice you can choose. But on the other 2, to get them wrong, you choose, there's 3 choices to choose. So basically it's 1 times 3 times 3. But here's the problem with that. That's 9 choices, but here's the problem with what I did there. You could get question 1 wrong. Let's see, I'm getting one wrong here. Yeah. You could get question 1 wrong and get the other 2 correct. You could get, let's see, I'm sorry, I said that backwards. X is the number of correct ones, right? So you could get number 1 correct and miss 2 and 3. Or you could get number 2 correct and miss 1 and 3. Or you could get number 3 correct and miss 1 and 2. So there's actually 3 ways you can do that. So there's 3 ways that you could, and each way has 9 possible answer sheets that you could turn in for each of those 3 ways. So 3 times 9 is 27. If you don't quite understand that, don't worry about it, but there's 27 possibilities. On this one, you're getting 2 correct. So again, to get 2 correct, that means you're going to miss 1. So let's say you get the first 2 correct. So you got the first 2 correct and you missed the third one. Well, if you think about it, there's only 1 way to answer this one correct. There's only 1 way to answer this one correct. And there's 3 ways to answer this one wrong. But that's not the only way you could have gotten 2 correct and 1 wrong. You could have gotten the middle one wrong, or you could have got the first one wrong. So we have to multiply this by 3 to get 9 possibilities. And then to get all 3 correct, there's only 1 answer sheet that gets all 3 correct. Now what's interesting, if you add these 4 numbers up, they add up to 64. Okay? But now that I know this, I can calculate the probabilities. So now the probability of getting none correct is 27 out of 64. The probability of getting 1 correct is 27 out of 64. The probability of getting 2 correct would be 9 out of 64, and the probability of getting all 3 correct would be 1 out of 64. Notice if you add these probabilities up, they add up to 1. And that's always true when you add the probabilities of all the probabilities associated with a random variable. Now, with a random variable, all the probabilities, each of the probabilities must be between 0 and 1 inclusive, and their sum must add up to 1. Let's look at this one. Let's say 3 coins are tossed, and we're interested in how many land heads. Well, let's let X represent the number of coins that land heads. Well, then you could get none of the coins heads, or only one of the coins could be head, or two of the coins could be heads, or all three could be heads. Now, look at the random variable assignment. So if you get tail, 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 x would be 0 because no heads. Tail, tail, head, x would be 1. Tail, head, tail, x would equal 1, and so forth. And you can just read the rest of it across there. So now let's find the probability of each of these random variables. The probability of getting no heads, well, there's one way out of 8 to get no heads. What about the probability of getting one head? Well, there's 1, 2, 3 ways out of 8 to get one head, so that's 3 out of 8. What about 2 heads? Well, there's 3 ways to get 2 heads. And let's see. I think I hit the wrong one here. Hang on just a second. This is one head. These are the 3 for one head. Okay? And then these 3 here are the ones that have 2 heads in them. Okay? So that's 3 out of 8 as well. And then the probability of getting all 3 heads, then there's only one way that can happen out of 8. So that's called the probability distribution of our random variable x. Now, once you have the probability distribution, you can easily get the what's called the expected value. Now, the expected value of a random variable is what's expected in the long term. So, you know, like if you sample just a few families, you might get an average of only 1 child per family. But if you actually sample a large population, then maybe the average is more like 1.5 children per family. So it gets closer to the average the more that you sample. But basically, to calculate the expected value of a random variable, you just, once you have the probability distribution table like this, then you just take each x and multiply it by its probability. So here, I would take 0 times 1/8, and then I would add to that 1 times 3/8, and then I would add to that 2 times 3/8, and I would add to that 3 times 1/8. And when I add those all up, I get 12 out of 8, 12/8, which is 1.5. So what this means is that if we did this experiment over and over and over and over, like maybe we did it 1,000 times, and we counted up how many heads we got, we should average 1.5 heads per trial. So that's what we should average if we do this experiment a large number of times. Now go to our test example. This was the probability distribution for our quiz, or test, whatever you want to call it. So take 0 times 2764, and then 1 times 2764, then 2 times 964, then 3 times 164, add that up, and you get 48 out of 64. So if you took this quiz, say, 1,000 times, or if 1,000 people took the quiz and they were all guessing, then we would expect them to average less than one correct question per trial. And so that's what that means. So in other words, don't guess on a test. Make sure you study so you don't have to guess. Now I'm going to end this here. I do want to make one comment. Expected values are not probabilities. They can be greater than 1, they can be less than zeros. And so what I'm going to do in the next video on this section is I'm going to pick up on some examples of calculating expected value, because there's several different ways that we can approach expected values of a random variable.